this is quadratic functions in polynomial form.
It's a shrink, right?
What kind of shrink? Horizontal or vertical?
The vertex wouldn't change, right?
Right. It would just kind of raise all the lines up. That's because we also have an x to the equation. All right. Now, I think. Boom! What happened?
When a becomes negative, it inverts the graph.
And well, what's going on there?
Oh, when a is 0, it's a line.
What happens when a equals 0? It's a line. Okay. All right. So let's get back to what I want to be.
So just wait, it's moving it around the x function.
Yeah. It's moving it around the y-intercept.
Does it change the y-intercept?
No.
No. Change the vertex, right?
Yeah.
So the coefficient x does affect the vertex.
Just changes the y-intercept.
Right.
So C is the y value of the y-intercept.
Yeah.
Oh,
Yeah.
okay.
We're going to have to splice this all. Oh, yeah. But this is quadratic functions in standard or vertex. Start with your finger and slide it around. Whoa! Yeah, I can help you out there. Move the slider around. There you go. There you go. See how it's changing? Whoa.
Yep.
Sometimes it answers, sometimes it doesn't. Okay, so let's go down to H and K. Slide that around. It's changing the H. Slide the K around. What does slide the K around do, Libby?
Y values. Changes the y values.
How does it change the shape?
Here with quadratic functions and models. And first, a quadratic function is a kind of polynomial function. And one of the key things I want you to notice in this definition is that n has to be a non-negative integer. A non-negative integer. What this results in, if we do this, if we make all the powers in x like 2 or 5 or 8 or 0, then we end up with a domain for all polynomial functions of all reals. Now, we're going to specifically focus on a quadratic function today, where it's like a polynomial, but we just focus on n equaling 2. So the degree is 2. So this is also called second degree polynomial. Second degree polynomial function. Okay? It's also called a quadratic function. It's called the concavity. I'm going to put a little happy face here. See how it looks like it's happy? That means it has a positive attitude, or a is greater than 0. Happy parabola. Over here, we've got our sad parabola. See the sad face? See it frowning? And the a is less than 0. But notice how negative b over 2a is the coordinates of the minimum, or the maximum. And instead of a minimum, if a is greater than 0, it's happy. So if it's happy, it has a minimum. If it's sad, it has a maximum. Okay? H of x equals x squared minus 8x plus 16. And we can try and get it into standard form. In fact, you might notice that this is x minus 4 quantity squared. That is so handy, because we get our vertex right away at 4, 0. And so we can just graph it as 1, 2, 3, 4. And 0 goes way up here to 16. Our axis of symmetry is here at x equals 4. We're good to go. Let's try another one. Okay, here's f(x) equals 1/4 x squared minus 2x minus 12. Well, let's take the shortcut from standard form, and that is that the x coordinate of the vertex will be negative b over 2a. So negative 2 over twice a fourth is 4. To find the y coordinate of the vertex, we can put 4 into the function. F of 4, so that's 1/4 4 squared minus 2 times 4 times 12. So x is at 4, negative 16. We also have from the standard form right away the y-intercept. The y-intercept is just 0, negative 12. And this also gives a point symmetric to that at, if the axis of symmetry is at 4, then there's going to be a symmetry point at 8, negative 12. So let's get these plotted so far and see what we've got going on. Okay, so I've plotted the 3 points so far. The vertex here at 4, negative 16. The vertex here at 4, negative 16. And then the y-intercept and the point symmetric to it. Y-intercept at 0, negative 12, and the point symmetric to it at 8, negative 12. For a couple more points, let's plot the actual x-intercepts, because it looks like it's going to have x-intercepts. Now to do that, we've got to take the original equation that originally came up with our x-intercepts. So first of all, I'm going to multiply through by an LCD equal to 4 to get rid of that fraction in front there. And I'm using the LCD in the equality sense. So multiply both sides of the equation by 4. So 0 equals x squared minus 8x minus 48. So we have to look at factors of that. I'm going to do completing the square. So half of 8 is 4, 16. Add 16 to both sides. And so you get 50, you get 64. Well, I guess we could have factored this, x minus 4 squared. So x minus 4 equals plus or minus 8. These plot our previous graph. Negative 4 there, and I think the other one was 8. No, the other root was 12. So let's find 12. 4, 8, 12. There we go. And that looks like a pretty good parabola graph. Let's check with your calculators or GeoGebra and see what that comes up with. Fill it in a little bit so it looks better. Beautiful. Don't lose those points. Those are key. Roots at 12, 0, and negative 4, 0. X, Y axes. And look at that, GeoGebra agrees with me. Okay, next. Now let's try to do a problem where we actually create the equation of the parabola from given information. Here, the vertex at negative 2, 5, and a point at 0, 9. So here on 47, you got the vertex is HK. So H equals negative 2 and K equals 5. So we're pretty much set here. We just have one unknown constant in the vertex form, y equals A times x minus h squared plus K. We can fill in h, which is negative 2, so x minus 2 squared, plus k, which is 5. Now we can use the other point, 0, 9, to figure out what a is. Put 9 in for y and 0 in for x, because this was minus and minus 2, remember. So we get 9 equals 4a plus 5. So 4 equals 4a, so a equals 1. So finally we get y equals a, which is 1, times x minus a minus 2 squared plus 5. Or more simply, y equals x plus 2 squared plus 5. 0, 9 goes through it, and it's got a vertex at negative 2, 5. Okay. Path of a diver. The path of a diver is given by this formula, where y is the height in feet and x is the horizontal distance from the end of the diving board. What is the maximum height of the diver? Well, that's going to happen at the vertex. And it looks like we got a big negative in front here, because that makes it go downward. So the maximum height of the diver will happen at the vertex. Oh, God. And the vertex is at negative, the x-coordinate is at negative b over 2a. So at negative 24 ninths over twice a, which is negative 4 ninths. So we get the negatives canceling, the 9's canceling, and so you get 24 over 8, which is 3 at 3. So the max height would be the y-coordinate of the vertex, which will happen at negative 4 ninths times 3 squared plus 24 ninths times 3 plus 12. So we get negative 4 plus 8 plus 12. 20 minus 4 is 16. So the max height of 16 feet. for the diver. Let's check this on GeoGebra. And sure enough, GeoGebra agrees with me with the max height here at the vertex at 3,16. Finally, let's look at this word problem, max revenue. A small theater has seating capacity of 2,000. When the ticket price is 20, attendance is 1,500. For each dollar decrease in price, attendance increases by 100. Write the revenue as a function of the ticket price, X. Well, the first thing I'm going to do here is I'm not going to write that as the ticket price. I'm going to change the name of the variable, okay? Just because it's going to be easy for you to conceive the problem. If instead we let X equal the number of $1 decreases. X equals the number of $1 decreases. So now we start talking about revenue. Revenue is ticket price times tickets. Number of tickets sold times the ticket price. Times the ticket price. So, in this case, number of tickets sold is, we start off with attendance at 1,500, but we're going to lose 100 people for every dollar decrease. So we're going to lose 100 times X. X is the number of dollar decreases, so we're going to lose that many. Now, the ticket price, though, we increase for every X that we decrease the price by. Now, the ticket price itself, though, X is the number of decreases, so we can come up with a price of $20, but then we're going to subtract off X. X is the number of dollar decreases. So if we have $5 decrease, it's going to be 20 minus 5, or $15. Now, the easiest way to analyze this function is to look at it in factored form and find the two roots. Okay, here's something off of GeoGebra. I just did it so I get a nice accurate view of where these roots are. When X equals, the roots will happen when R equals 0. And so if we said 20 minus X equal to 0, we get X equals 20. So that's one of the roots right there. And if we said 1,500 plus 100x equal to 0, we get x equals negative 15, which is the root over here. So let's figure out, where is that axis of symmetry? Well, it's going to be halfway between the roots. So the x-squared of the axis of symmetry will be equal to the average of the roots, root 1 plus root 2 over 2. So you get negative 15 and 20 over 2, or at 5 halves, which is 2.5. Now this means we're going to maximize our profit, maximize our revenue at 2.5 $1 decreases. So let's put 2.5 in the equation. 1,500 plus 100 times 2.5 times 20 minus 2.5. So we're down to $17.50 for the price of the tickets. As a result, our numbers have jumped up here, and that's going to be $2.50, $17.50 then, for a price there. And you multiply those two together, and you get our grand total now of $30,625 for our maxed income. And that compares favorably on the graph there. See how we just go over 30,000 there at the peak. Flange out.